Welcome to Season 2, Episode 2 of the now quarterly lecture series, The Geophysical Exploration of Ocean Worlds and Links to Habitability. NASA has formed the Network for Ocean Worlds, or NOW, to advance comparative studies to characterize Earth and other ocean worlds across their interiors, oceans, and cryospheres, to investigate their habitability, to search for biosignatures, and to understand life in relevant ocean world analogs and beyond. Season 2 of the lecture series explores the science motivations for ocean worlds exploration. In this episode, Dr. James Roberts and Dr. Angela Marusiak discuss the science motivations for geophysical exploration of the ocean worlds and how to execute such objectives.
All right, thank you very much. In some ways, I have the easier job here today because I just get to ask a laundry list of questions, and Angela's the one who has to come up with ways to answer them. And so this is what we're talking about is what do we want to find out here? What is our goal? And of course, as it always comes down to, it's about the most delicious treat ever created by humankind, and that is the Cadbury egg. Oh, it is a delicious confection that has a chocolate shell over a creamy interior, and you can only get it seasonally, right? And this is, in fact, very much like an icy world, which has a brittle, icy crust over a creamy or liquid water ocean, and they also have seasons. The difference is you should not actually try to eat an icy satellite. It is not going to go good. So our knowledge of ocean worlds depends really on how much we've explored them. So on the left, I have a graphic showing some of the ways we would like to characterize them and some of the ones that have been studied. I have Enceladus, Europa, Titan, and Triton on here. And you can see that in Enceladus, we have a lot of progress already in identifying it as an ocean world and characterizing the ocean. But assessing the habitability is not as far along. And then some of the others, like for example, Triton, we can't even be confident it's got an ocean at all. So another big unknown here is that where's the energy coming from? What is the source of all the heating? So on the right is a graphic showing where the heat is coming from in these. So the brown shows that it's radiogenic. And the blue and purple are tidal energy, either in the ocean or in the ice shell itself. And so you can see, like, Enceladus is entirely tidal energy, and I'll get into that a little bit later. Europa is mostly, but it's got a significant amount of radioactive elements in it. And in general, it looks like the more tidal heat you have, the more likely you are to have an ocean. If you drop down below a critical amount of heat flux, you simply can't sustain liquid water anymore. And what's interesting about Triton is that we really don't know where on it is. They're showing three different possibilities here. So the heat sources that we're mostly interested, there's three of them. There's radioactivity, and you're generally only going to find this in the silicate part of the planets. You have tides, which is where the body deforms over the course of each orbit, and any movement that is not elastically recovered is dissipated as heat through friction. You can get a lot more tidal energy going on if the ice shell can deform, and this is usually accomplished by having an ocean underneath there. And then, of course, there's the most fun source of heat, which is an impact. And that's where you have a shock wave, heats the interior, boom, into that ice shell, and not only does it wreck up the place, but it also deposits a lot of heat in there, and it can influence the deeper dynamics by creating some sort of transient ice shell convection. So tidal heating, these are highly exaggerated plots showing Europa orbiting around Jupiter. You can see that it gets stretched and squeezed as it moves closer and farther to its host planet. And some of this energy is just recovered elastically, like bending and releasing a rubber band. But if you try that enough, you're going to find that it breaks. And so some of that is dissipated into the interior. And that really is the source of all the energy that causes interest in ocean world. The tidal heating also comes in two flavors. There's a obliquity tides, which is caused by the satellite having an obliquity. This tends to drive sloshing around in the ocean. And then you have eccentricity tidal heating, which is stretching and squeezing like this. And that tends to get focused in the solid parts, mostly the ice shell. And as you can see here, they can have vastly different patterns, depending on which mechanism is dominant. So what I'm showing here is a variety of the ocean worlds or probable ocean worlds that we know of in the solar system. You can divide them into two categories. One where you have a relatively thin water layer such that you have an ice shell covering a liquid ocean that is in contact with rock underneath. And then you have the larger ones where you get to such intense pressures underneath the ocean that you're actually able to sustain higher density ices. It's still water ice, but it's got a different crystal structure that makes it more dense than water. And so here you have an ocean sandwiched in between the ice layers. Now, for our purposes, I'm mostly going to focus on these three objects because there's simply too much to get in a 20-minute talk. And the reason this is so interesting is that when the liquid ocean is in contact with rock, you have a lot of interesting chemical reactions, and you have ways to get heat directly into the ocean through volcanic seafloor vents and things like that. And so that's really important for habitability. And you can look at Europa, where you have a variety of surface features like these ridged plains, chaos terrains, and lenticulae that point to some kind of dynamics happening deeper down. You also have impact craters, and while they don't tell you that much about the interior, the fact that you see so few of them means that the surface is very young. Inside the interior is the classic cutaway model of the ice shell, very thin over an ocean, over a fairly large silicate planet. So Europa isn't even an icy world at all. It's a rocky world masquerading as an ice. It's trying to trick us, thinks it's funny. But in fact, even with that small layer, it's still got twice as much water as Earth. Europa also has a lot of magnetic field to deal with. You can see here this image of Jupiter's very intense magnetic field and Europa traveling through it. And this is in fact how we know that Europa has an ocean, because that magnetic field induced an opposing field in an electrically conducting layer inside Europa. The only plausible thing that could be is a briny ocean. Interest of time, I'm going to skip over some of these. They're really great images, but we just want to get to some more of the geophysics here. It looks like Europa may be the only other planet besides Earth that we know of that actually has plate tectonics, where you can get ice subducting underneath other ice plates. But because the density difference is far less than you have on Earth of different types of rock subducting under others, it doesn't go very deep. And eventually it just gets warm enough that it gets subsumed into the interior. So you don't have these deep plate trenches like you have on the Earth. If the ice shell is thick enough, you can actually have solid state convection, where it moves heat from the interior very efficiently upwards by transporting the buoyant material up and releasing the heat to the surface, sort of like what happens in a lava lamp. You see these pull-apart bands on the surface that point to some kind of extensional mechanism. This is sort of the extensional plate tectonics we're talking about, and this could be driven by convection in the interior here, where this upwelling plume is just pushing the surface apart. And we have these chaos regions, which are just these dramatic broken up terrains, and we really don't know what's causing them. But one leading hypothesis is that it's actually pointing to a brine pocket in the ice shell underneath it, and the surface material is just sort of caved in and collapsed, and that's why it looks all jumbled up. The second moon I want to talk about today is Enceladus. This is my zoom background here. This is one of my favorite images because we are showing this to scale. Enceladus will actually fit in the North Sea if you put it there. I don't recommend it because that could cause some other problems later. But even though it's such a small moon, it's got a lot of activity. There are these plumes of vapor and ice coming out of the south polar region. If you look down on that region, you see a large excess of heat flow coming out of there, especially along these four fractures known as the tiger stripes. But there's no corresponding thermal anomaly in the north. So how does a body this small, with relatively little possible tidal heating, keep it solid? Because even with the tidal heating you would expect to get on there, an ocean on Enceladus would generally freeze in tens of millions of years. It just doesn't last that long. So people have considered that you could put in various salts or even ammonia in the ocean. Those are common minerals, and that can depress the melting point possibly by up to 100 degrees if you use the eutectic composition, and that can slow down the freezing rate. But we don't really know how much ammonia is in the ocean or what that's going to do to the ice rheology. And a bit of a problem with this that I want to make a point of is that if you add ammonia into the ocean, you're reducing the density of that ocean. And any solution that's above about 15% ammonia is going to be less dense than the ice. So the ice shell will break up, delaminate, subduct, basically sink to the bottom. Not going to go good. So practically the freezing point of the ocean on Enceladus can't be less than about 230 Kelvin. So you might ask, do we even need an ocean on Enceladus to explain that? I mean, we have this classic layer structure of rock, water, ice on here, but it's very small. And it forms too late for there to be really any melting of the silicates. It's just not enough radioactivity. And the pressure at the center of Enceladus is similar to the pressure at the surface of Venus. You are not squeezing anything together at all. So what you might have is just a rubble pile core filled with ice. And even without an ocean, this can deform. You can also have a regional sea. This tends to be easier to sustain in a global ocean. But then you have to ask, how do you get this asymmetry? How does something like that get started? You'll notice that if you want to use tidal heating, here's an example of the tidal heat pattern. It's always symmetric about the equator. There's nothing to tell north from south here. But the only activity is observed at the South Pole. So I suggest we might use the last refuge of the scoundrel and say an impact did it. Oh, how convenient! A theory about geophysics. It doesn't require looking through a telescope. Get back to work. Yeah. But we have been looking at simulating impacts that can punch all the way through the ice shell and looking at how long that heat can remain. And we're now looking at evidence that the depressed south polar terrain could in fact be the remnants of a giant impact crater. The last thing I want to go into before my time is up is to consider whether Triton could be an ocean world. We've only seen this once with Voyager 2, and that was a pretty distant flyby. And we learned that Triton is really weird. First of all, it orbits retrograde, which implies that it must have been captured into the system in initially a very eccentric orbit. But this would circularize pretty quickly because the tidal influence would just draw it down like this, and it would dissipate an enormous amount of energy into Triton, which could still be held there today. When Voyager flew by, it did image 4 active plumes, but we don't know if this is pointing toward heat in the interior or if it was just active surface material coming up there. But the surface is very young. Surface age is probably no more than 10 million years. So there could be these tectonic patterns here could be driven by interior dynamics. The magnetic field is also pretty interesting, and I think this is the last graphic I'm going to show. So you've got Neptune here, which itself is tilted with respect to the ecliptic, and it generates a magnetic field, which is also tilted with respect to the spin axis. And what's even worse than that, it is offset from the center, up there. So now you've got Triton orbiting around it, but nope, not on the ecliptic. It is also inclined at some punkerish angle. And so it is now orbiting through this rapidly changing magnetic field. And we've actually observed from Voyager these fluctuations, which could be evidence of an induced magnetic field inside Triton, which would require an ocean. So the takeaways from this talk is that there's ocean worlds all over the place, but they're all different. You can't really say ocean world is one kind of thing. We've learned a lot from these survey missions, Voyager, Cassini, Galileo, that have explored these, but really we have more questions than answers. So we need to go back with dedicated missions looking specifically at these. So we have Europa Clipper right now in development. There's a lander being looked at. I know Shannon has done a study on the Enceladus Orbilander to look more at that. And there have been studies, Triton, unfortunately, just lost out to go back to the Neptune system. But there was another concept study, Neptune Odyssey. And I want to thank the authors of all these studies, because that's where I got a lot of the graphics that I've shown from this. And there are three investigations that I think are key at getting to the interior structure and dynamics that any of these missions should consider. Magnetic induction, which can tell you how deep the ocean is and what its salinity is. Radar sounding, which can actually tell you how thick the ice is. And tidal deformation, which gives you a combination of the thickness of the elastic cold part of the ice shell and the rigidity of that material. And so that's all I have, and I'm happy to take questions whenever.
James perfectly led into the talk, especially with his last talking point. I should mention I'm a seismologist by training, so I'm going to be slightly biased when I also argue that seismology should definitely be included on lander missions. And very much like James's talk, I'm going to focus a lot on Titan, Europa, and Enceladus for the geophysical exploration of habitable worlds. And I'm going to try to connect how each instrument can help us assess habitable conditions, environments, and answer a lot of the science questions that James brought up. So I'm going to go over a couple of instruments fairly quickly and not too much in depth, just so that you can see a broad spectrum of the different types of geophysical investigations that can help us look at icy ocean worlds. So now you might be asking, why is geophysics so important, especially for habitability? Isn't it much better to just send biological or chemical investigations? But I like to argue that beauty is a little bit more than skin deep. So a lot of NASA missions do a great job at looking at the surface of the planets, but it's really hard to see what's going on inside and what makes these worlds really tick. So geophysics helps us do that. And specifically, it can help us look for habitable environments and conditions. So with geophysics, you can look at global scale features. So you can answer, how thick is the ice shell? How deep does the ocean go? Are there high pressure ices? Does Europa have a metallic core? And you can start to assess internal layers, but you can also look at the local scale. So James brought up a lot of great examples. So for example, the chaos terrain, if you want to figure out, is there in fact liquid water beneath the surface, geophysics can help with that. And additionally, it can help answer a lot of questions about dynamics of both the surface and the interior. So things like, is the ocean convecting? Is the ice layered? And you can start to put constraints on things like composition. And overall, it leads to a better understanding of the current conditions, which can help us better understand how did these bodies evolve and are they stable over long periods of time for, say, life to evolve. So there's a lot of different science goals that a geophysics mission might want to answer. And Jonathan Lunan had this great figure in his 2017 paper that I show here that shows how Clipper and the European Space Agency's JUICE have different instruments that can help answer some of those questions. So the main ones are going to be the physical state, layering, and motions within the cryosphere, and also the hydrosphere, basically the subsurface ocean. It can answer things about the surface activity. So do you have active rifting and faulting? How is material transported, say from the water rock interface up to the water ice interface and possibly the surface? As James mentioned, tidal dissipation is really important, and hopefully we can answer questions regarding that. Exactly how does the tides dissipate between the ice, liquid, and silicate interiors? And is there activity at the water rock interface? So for example, with Enceladus, there's been analogies to maybe it's hydrothermal. So geophysics might be able to help answer the question. So the main techniques and approaches I'm going to discuss today are imaging and altimetry, electromagnetic approaches, radar sounding, gravity, and my personal favorite, seismology. And I'm going to be discussing 3 missions quite a bit, the Europa Clipper mission, as well as ESA's JUICE, which will do flybys of Europa and the Jovian system, Dragonfly, which will head to Titan in the 2030s, and will carry a suite of geophysical instruments, and then mission concepts such as the Europa lander, as well as the Enceladus orbit lander. So just to give you an idea for each approach, I'll give a brief history and why it's important and how we hope to include it in the future. So to start off, there's imaging and altimetry. So 2 of the most famous examples are MOLA and LOLA. And these are high-res topography of both the moon and Mars. So as an example here, I have MOLA, which mapped Mars. There's also LIDAR and INSAR, which can also kind of go into this category, and INSAR will be included on the Veritas mission, which was just selected. They'll also make appearances on future missions. So there's the ICE instrument aboard the Europa Clipper, which will image the surface. JUICE has GALA, the Ganymede laser altimeter. And then Europa Concept mission might include LIDAR to help it choose a landing site. And what these instruments hope to do is provide constraints on surface topography and current conditions. So very much like the LOLA maps shown here, they can map out with high precision what the surface looks like. So they can point out if there are craters, the topography of chaos terrain, rifting, the tiger stripes on Enceladus, and they can also search for recent geologic activity. So for example, depending on the lifetime of the mission, they might be able to point out, is there active faulting, were there recent impacts, and what is the resurfacing rate of some of these bodies? And through different approaches, they can also measure things like vibration, obliquity, and love numbers, which can help point back to structure of the bodies. So the main science goals that imagery and altimetry can help answer is how thick is the ice shell, what's its structure made out of, and what are the different tectonic and geologic settings? So do you have active plate-like motions, or is it like other bodies that we've seen in the solar system where plate tectonics may not exist? And overall, for habitability concerns, they can help answer how is material moved within the ice shell and ocean. For electromagnetics, they have been absolutely crucial for icy ocean world exploration. And Cassini and Galileo are 2 great examples, because they were able to basically confirm that we know that there's a subsurface ocean because of the magnetic fields that we were able to see around Europa and Enceladus. And upcoming examples are going to include the Europa Clipper magnetometer, as well as a JMAG aboard JUICE. And these will hopefully go back and reconfirm some of the findings of Galileo. This is a figure that one of my co-authors came up with. So in addition to using a magnetometer aboard a flyby or orbital mission, you can actually land instruments on the surface. And what these might be able to do is measure things like resistivity, or as shown here in the figure, conductivity, as well as induction response. So different materials are going to have different conductivity. So if, for example, on Enceladus, you had a direct conduit between the ocean and space where the plumes are, you might be able to see that through the surface stations where they measure the different conductivities of the materials. So the science goals that electromagnetics can help answer are, what are the ice and ocean structures, both on a global scale, as well as local. So they can go to the tiger stripes and see if they can see the different conduits and figure out precisely how is material transported from the subsurface ocean to the surface. It can also provide constraints on convection, whether or not it's occurring, as well as composition. So it might be able to answer questions about how salty is the ocean. And this can be really important for Europa, where there may not be active plumes, so it's difficult to actually constrain what the composition of the ocean is. So electromagnetics can help us determine if there are habitable conditions in the deep subsurface ocean, but also in possible near surface pockets or conduits. James also mentioned radar. And radar is really great for looking into the ice shells. So depending on the frequency of your instrument, it depends your resolution and as well as your depth. So two examples I have here are the MARSIS and SWRI instruments aboard the Mars Reconnaissance Orbiter, as well as Mars Express. And because they have slightly different frequencies that they look at, MARSIS is able to see a nice reflector at the Mars South Polar terrain. And of course, whenever you're talking about radar, you have to bring up Venus, because without radar, you can't really see through the clouds. And this is also a similar case with Titan. Because Titan has a methane-rich atmosphere, it can be difficult to see through the clouds with typical imaging. So by using radar, you can get a better sense of what the surface looks like. And of course, it will be included as well on JUICE and Europa Clipper as the rhyme and reason instruments that are paired together. And what they hope to do is look at things like ice ocean reflections. So we can determine how thick the ice shell is and if it's consistent globally by looking at these radar reflections at the ice ocean interfaces. So by looking at reflections, absorptions, and scattering properties, we can look at global scale features, but also look at things like the chaos terrain to see, are there pockets of liquid water close to the surface? And perhaps those are better environments to look for life because they don't require drilling through kilometers of ice, but maybe only a few kilometers or meters. So with radar, we can search for habitable environments, both in the near surface and a little bit into the deeper interior. Although I should mention radar has some difficulty seeing through liquid water. Now with gravity, there's been a couple of different missions. So some have been specific gravity missions, such as GRAIL, which looked at the moon and is pictured here. Excuse me, that's not. Yeah, that is GRAIL. Sorry, my apologies. As well as GRACE that has looked at Earth. But then you can also measure gravity in different ways that doesn't necessarily require a specific instrument, and that's what the Mars Reconnaissance Orbiter, Odyssey, and the Mars Global Surveyor did in order to generate maps of Mars. And there's JUICE does have two instruments that will specifically look at gravity, and that's 3GM as well as PRIDE. So with gravity, you can measure things like the K2 love number, degree 2 gravity field, and you can identify areas where there's a gravity or density anomaly, both in the ice shell as well as in the water column. So this is a figure that one of my co-authors created, and it's for Enceladus. So what you're looking at is in the top, there's surface displacement, and you can see that it depends on whether or not you have faulting or a variable ocean. You can also look at it through tilt, but with gravity, you can also see whether or not there's a deformable core within Enceladus. So you can get a lot of different types of information from gravity. And by creating gravity maps, you can help point out regions where there might be anomalies from, say, water lenses or different types of material beneath the subsurface that you can't just see by looking at the planet. And it helps us constrain not only internal layers, but also some of the dynamics and help answer questions on why exactly is the South different than the North on Enceladus, which, as James brought up, is a really important science question. So maybe we can provide more evidence that Enceladus was hit at the southern pole. Right, so in terms of habitable conditions, we can search for environments and also answer questions about how is material actually being exchanged through the different layers. And of course, this is my favorite, as I'm slightly biased being a seismologist myself. but seismology has been really, really critical on Earth, as well as a couple of other missions. So notably, there's the InSight SEIS instrument that's currently on Mars and is detecting Mars quakes. And there's also been the Apollo seismic packages. So on the moon, one of the key findings from the Apollo seismometers is that most of the detected moonquakes were actually deep moonquakes. And because we had a lot of stations that were set up only on the near side, we did detect them only on the near side. So there's hopefully one of the questions that will be answered by the newly selected far side seismometer is whether or not these deep moonquakes are global or if they're sort of biased towards the Earth side. So by detecting these deep moonquakes, we're able to answer a couple of questions about how does tidal dissipation occur on a body like the moon. And as a reminder, the moon is roughly the same size as Europa. Of course, the different materials, namely the fact that the moon doesn't have an icy shell and ocean, will probably change how tides are controlled. But also on Earth, seismology has been really critical. So it provided one of the key pieces of evidence for plate tectonics as well as mantle dynamics. So as James brought up, there's this possibility that Europa may have plate-like motions and might have subsumption. So with seismology, if we're able to detect ice quakes at different depths, we might be able to point to whether or not subsumption is occurring. On Earth, seismometers have also been deployed to cryospheric studies. So we've been able to map things like glacier structure and how the glaciers move through time. They also have been really important for anthropogenic and wildlife signals. So seismometers deployed in different environments have captured things like elk running by or two curious bears, unfortunately destroying equipment. And they've also captured things like whale noises. Now, I am not suggesting that there's elk and bear on the surface of Europa. That would be a little bit ridiculous. But I bring it up to mention that a seismometer essentially is like a microphone for the planet. So it can record things like ice cracking, and it might be able to detect deep quakes coming from the silicon interior, as well as possible unexpected sources from the ocean. And it will be included on Dragonfly as part of the DragNet instrument suite, and it has been suggested as an instrument for concepts, including the Europa lander, as well as the Enceladus Orbolander. Now, seismology, what it can do is look at reflections off the different layers. So here's an example of how seismic waves might travel through Europa. So they might reflect off the ice-ocean interface, which is a little hard to see here just because it is to scale and the ice is quite thin. In this example, the ice is only 5 kilometers thick. But it can also look at reflections off the ice-ocean interface, as well as detections off of the core. So we can answer whether or not Europa does have a metallic core. It can look at things like scattering and travel time anomalies to help answer, is the ice shell homogeneous, or does it have pockets where it's a bit different? And lastly, it can also answer general seismicity. So when I talk about seismicity, I mean where, when, and why are the quakes occurring? So we expect that over a tidal cycle, the amount of seismic activity is likely going to change. So we might be able to see that change in activity and where the activity is coming from. It can also answer things like, is subsumption occurring? Is plate-like motions occurring? What exactly is the activity going on near the tiger stripes? So there's a lot of key pieces of information that can be answered through just a single station, or if possible, seismic arrays. So seismometers are really important for not only answering, global structure and local structure and dynamics, but also the tectonic setting as well as surface activities that we might be seeing. So they might be able to locate habitable environments, but also answer questions about the conditions of those environments. And I also want to bring up that in addition to sending instruments to these other bodies, it's really important that we continue doing both lab studies and analog field studies. So through lab studies on Earth, we can create better data sets, which allow us to better model what might be going on at these conditions at other worlds. And if we have a better data set and better model, we can better understand the observations that we currently have, as well as the expected observations that we might have. And with analog field studies, not only are you allowing, grad students like myself to get out of the office and go to some neat places, but it helps test out equipment and approaches and different methods. So for example, here, this field study was looking at Can a seismic experiment work as well on, say, a Europa lander if it can't be coupled to the ground, as opposed to a traditional burial? So those are key questions that we'd want to know, as we're starting to build these concept missions, and we'll know what to expect once we get to different places. So it's important not to only, focus on the data that we do have and we might get, but also, help prepare ourselves so that the data that we get is optimal. So to summarize, geophysical approaches are really, really important for getting the internal structure as well as the dynamics of the surface and interior, tectonic and geologic settings, and looking for these habitable conditions and environments. And what I really want to reinforce is that the geophysical instruments work really well together, and they should be included together. So for example, if you have a seismometer as well as LIDAR or INSAR, if you have a seismic event, you can go and look at your topography data and see if there's any changes. So you can see if maybe the seismic event you saw was a small ice quake, or maybe it was an impact, or if it's faulting at a nearby region. And not only does it help better to tell you, what caused that seismic event, but where did it occur? That way your seismic data is better constrained. You can also use gravity with E&M and seismology all together to look at smaller features that might be difficult to see with only one of those instrument suites. So it's really important as we go forward to think about how do all of these instruments, work together in a way, because, they're greater than the sum of their two parts, so to speak. So if you're interested in looking at more than just, skin deep beauty, I would highlight that geophysics is really, really important, and helps put a lot of, or helps provide context for the other data sets that we might be seeing. And I just want to give a quick acknowledgement to the grant that's currently funding my postdoc, as well as my numerous co-authors. We have a paper that's currently in revision that discusses a bunch of these different geophysical suites in a lot more detail. So if you're interested in a specific instrument or approach, hopefully once this paper is, fingers crossed, accepted, it can help answer some of those questions as well. So thank you for your time. And if you have any questions that can't get answered right now, you can feel free to reach out to me via email or on Twitter. Thanks.
Awesome. Thanks so much, Angela. This was really great. I don't know if you guys tagged up beforehand, but that was a really nice synergy between the two topics. So well done.
No, but in retrospect, we should have, and then we could have.
It did work out really well. Like your last slide was like perfect. So
yeah.
But like I totally failed to mention seismology at all. And if you're landing, that's the one thing you want to do. Right.
That just paved the way for Angela to talk about her favorite science.
Yeah.
So for the question and answer session, since we have a lot of people online, I think what we're going to do is have folks raise their hands if they want to ask a question, and then I will put on my best grade school teacher hat. And oh, Angela, you were right on time. I'll put on my best grade school teacher hat and call on folks. So while everyone is thinking about their question, I'm going to go ahead and use my host's prerogative and kick it off. One of the things that gets me so excited about geophysics is the potential, like the contextual information that Angela was talking about that could help us understand the evolution in time of the ocean worlds, because I think time is a really big unknown in our understanding of habitability, let alone these ocean worlds. Could each of you speak to how, like what the kinds of, time and evolution related questions geophysics can help us understand, or your favorite means of getting at, transport and how long that's occurring?
Yeah, I can go. I mean, I think Enceladus is sort of a key example of this, because we see what it's doing, and it really couldn't have done this for all time. It's simply too active, and it's putting out a lot more heat that possibly could be sustained long term. So we're seeing some kind of cycle that it maybe it's it's dissipating heat that gets stored and then it releases it all at once. Or if you like the impact thing, it's just a big transient phenomenon.
Yeah, to add, I think Titan is really interesting as well. Not so much through geophysics, but there's this issue where if we look at the current methane outgassing, it seems like Titan should have lost its methane long ago. So it's kind of interesting to see, is that methane being replenished through like clathrates in the interior, or is this sort of a new phenomenon that's occurring within Titan's history? And Titan's also really interesting because it does have such an abundance of liquid methane on its surface. Maybe life could evolve around methane instead of like liquid water or something. So with geophysics, one of the questions I'm really interested in answering is, can we look at the composition of Titan at depth so we can answer questions on, does it have a high pressure ice that might change how material is exchanged between a silicate interior and the ocean if you have kilometers thick ice blocking it? Are these clathrates present throughout the ice shell, or maybe are they only at the surface? And of course, looking at things like cryovolcanism, is that another way that we might be changing the methane cycle over time? So yeah, that's what I'm particularly interested in at the moment.
Well, I'm also Titan biased, and I'm particularly interested in those as well.
And I wanted to follow up on one other thing, is that we think of these interiors as ice shell, ocean, lower down stuff. A lot of people just sort of ignore the mantle and core distinction, and it's just rock. But there's no reason to think that's constant through time. So that's something I'm looking at now, is how to actually properly treat melting of the ice shell and freezing of the ocean, and especially as tidal heating is concerned. If you ever freeze an ocean entirely, then you have locked the ice shell onto the silicate mantle underneath, and it's much harder to deform once you've done that. So if you ever get into that situation, it's really hard to get out of it. So, what is the mechanism by which the ocean is maintained, at least in part, over geologic time?
Yeah, James raises a good point, because if the ocean is fairly new, that has a lot of implications for habitability, because life is going to need, or at least we think, is going to need time to evolve. And if your oceans are short-lived or periodic, that might be shutting down the possibility of sustained life.
Or maybe that's the massive wet-dry cycle, the ocean world version of a wet-dry cycle. Thanks. Let's, it looks like Kevin Devine has a hand raised. Kevin, if you want to unmute and ask your question.
Yes, okay. Can you hear me okay?
Yep.
Okay, great. So calling from over in the UK, I love that photo of Enceladus, how small it is. It's smaller than our country. That's quite awesome, actually. It would fit in the North Sea between Britain and Scandinavia. But my question is about magnetic fields and indigenous magnetic fields on all of these bodies. We benefit from a great magnetic field here on Earth, which has helped to sustain life. It's protecting us from the influx of charged particles, which would also reduce our atmosphere over time. And that's what's happened to Mars. And the mystery about Venus is the mystery. Like Mars, it has a very weak magnetic field, yet it has a very thick atmosphere. But let's forget Venus, let's go back to the icy moons. Based on what we know about the intense tidal friction forces caused by the gravitational pull of Jupiter, and you've got a deep ocean, I suspect is it 60 miles, 60 to 100 miles deep? I'm not sure if anyone can clarify that. Then you've got the ice on top. You've got evidence, you say, of ice tectonics. I would expect, I may be wrong, that Europa has an indigenous magnetic field of its own, because it's got all the ingredients to produce a molten iron core, which I assume is the source of the magnetic field on Earth, plus lots of other heavy metals there as well. Is that correct? So, question for both James and Angela, and thank you very much for two fantastic talks. So, as I say about magnetic field, and also the mystery about Neptune's magnetic field. What's the source of it, and why is it asymmetric? Why is it not in the center of the planet?
Thanks, Kevin.
Well, I can start. The easy question is about Neptune's magnetic field, and that is, I have no idea why it's in that geometry at all. The more involved answer is about the magnetic fields on the icy moons. As far as I know, only Ganymede has its own internally generated magnetic field from an iron core. The fields in the other icy moons that have them is just an induced field caused by the salty ocean moving through the host planet's magnetic field. The good news is that we don't have to worry about atmospheric loss on anything except Titan, because there's no atmospheres to lose. And in terms of habitability, you are shielded by, several kilometers at least of ice. So it's probably reasonably habitable down in the ocean, but I would not want to be out on the surface of Europa.
Me neither. Angela, did you want to add anything?
The only thing I want to add is I think that is one of the goals of Europa Clipper is to investigate Europa's magnetic field a little bit to confirm whether or not it's purely induced or intrinsic. I can't speak to Neptune because I'm not 100% sure. But yes, I also agree with James that unless you want to die a really horrific death, you probably don't want to be on the surface of Europa for too long.
But at least it wouldn't take that long. I think you would die in an hour or something.
Yeah, it probably depends exactly where you are on the surface, but it would probably be like a day if you were unlucky, or weeks if you were really, really unlucky. But yeah, it's like Chernobyl level radiation.
Thanks, Kevin. It looks like Natalie has a hand raised. Natalie, if you want to go ahead and unmute.
Thanks. This question is actually for Angela. That was a really great talk, by the way. You kind of already touched on this, but what are your thoughts on EM versus seismic for constraining like specific different properties of interior composition? So like water versus like salts versus high pressure ice.
I would always like to argue that they should be used jointly and not necessarily pitted against one another. So with seismology, it would likely be a little bit difficult to constrain salinity at a high resolution, just because the primary way that we would back out a composition is probably like seismic velocities, which can be the difference between salty water and pure like water isn't that much different. You might be able to look at things like the amplitude comparison to look at oh, the word's escaping me right now. It'll come to me in a second. Anyway, my point being is seismology would be a little bit difficult to do it. So E&M might be the way to go to look at the differences in composition. But again, I want to reinforce that, you want to try to think of these as being used together rather than saying, oh, we can include a seismometer or an E&M. Which one do we want to pick?
No, thanks for that. Yeah, I was more curious on like which one is tuned for like specific problems, I guess, as opposed to like, should we pick one over the other?
Yeah, I would say seismology is really great at nailing down things like the brittle ductile transition, whether or not the ice is convecting. Like that is something that we'll be able to do. And especially because ice's seismic velocities are really tied to temperature. So like that's something great that seismology would be at. The composition of the ocean, not as much. I'm not saying it's impossible. I just wouldn't rely on seismology to do that alone.
Awesome. That was really helpful. Thank you.
I'm going to follow up on that question, Angela, because I think on your EMF slide, you had that nice figure. And did I see two like instruments that were each making a measurement? Like, do you need to have, thinking in a landed situation, multiple measurements at different places on the surface in order to get useful information from the landed electromagnetic field measurements?
Yeah, so the figure did have two stations, one sort of right above the conduit and another nearby. I think you could be able to get away with a single station, though very much like seismology, the more stations you have, the better, because you can corroborate data and be able to look at differences between the stations to assess differences. So, you know, of course, if budgets were an issue, you know, send all the instruments, but I think you could be able to do it with a single station.
That's good to hear, given the realities of, of missions. All right, I'm not seeing any other hands, so I'm gonna ask if there are any other closing thoughts you guys want to leave us with.
I mean, I think the main thing is that all these ocean worlds are different. And so we can't think we understand them in general just by looking at one. If you take what you know about the plume on Enceladus and try to use that to understand the putative plumes on Europa, you're going to have a bad time. So we need to investigate each one of these on its own.
Yeah, I completely agree with that sentiment. It would be like exploring Venus and then trying to explain Earth and Mars based on what you see at Venus. So yeah, I think it's really important that over the coming decades, we try to send as many missions to a diverse amount of worlds. And in the meantime, I think it is important that we continue with our modeling, field work and lab work. That way, once we get these data sets, we can really sink our teeth into it and try to understand it to the best of our ability. You know, it's great if we can start moving away from, well, assuming the ice shell is pure water, into something that's, you know, possibly, and I'm guilty of it too. But, you know,
you got to start somewhere.
Exactly, a little bit more based in reality would be fantastic.
Awesome. Well, thank you guys both so much. I hope you get a chance to see in the chat, people are expressing their gratitude for 2 wonderful talks, introducing us to the powers of geophysical investigations and importance of geophysical investigations at these ocean worlds. So thanks everybody so much for tuning in to this latest episode of the Now lecture series. Tune in again for episode 3 coming up in a few months. I should have looked up the date before beforehand, but you'll see advertisements coming out. And with that, I will end this session. Thanks very much.